Thank you everyone for coming to my talk. I'll be talking about the performance of the Scala Collections Framework. My name is Craig Motlin. I'm an engineer at Goldman Sachs. I've worked there for about 10 years on a number of different projects and teams, and for the purposes of this talk, my most relevant work is on a library called JS Collections. It is an open source collections framework for Java, not for Scala, but it has a lot of similarities with the Scala Collections Framework, and through working on it, I've learned a lot about performance. At Goldman, Java is very common and Scala is becoming more and more used. And I don't see Scala being used for special purposes, rather it's being used as a totally general purpose programming language for any kinds of problems. And that's great, but I still switch back to Java when I have performance concerns, and that's unfortunate. You should be able to just use Scala for whatever you want. And I know I'm not alone in this, because while researching this talk, I found this comment in red-black-tree.scala in the core libraries, where there's an explanation of why the inline annotation is used and some null checks. And the comment at the bottom says an alternative would be to implement this using plain old Java code. And that's familiar to me. And it's unfortunate. I would like to use Scala more widely. So my goal here is to highlight a few performance problems. I've seen other Scala talks about performance problems. These aren't necessarily the most important, but they do matter to me. And the focus here is also specifically on collections as opposed to the compiler. And I'm not just going to complain about them. I want to suggest fixes where possible and borrow ideas and technology from JS Collections where it's applicable. So I will be talking about how these libraries differ, but I should point out first that there's much more in common between them than different. Of course, the languages are different, but the ideas are the same. So in both libraries, we have mutable and immutable collections with a common parent. In Scala, they'll all have the same name, but they'll reside in different packages. In JS Collections, they'll have names like mutable list, immutable list, and list iterable at the top. They both have many high-level iteration patterns, and for the most part, they're gathered up at the hierarchy root. So that's traversable in Scala, and in JS Collections, we have rich iterable. And the names are sometimes different because we use the Smalltalk naming conventions in JS Collections, but the idea is map one-to-one. So filter is called select, map and flat map are called collect and flat collect. There's also a whole bunch of patterns that have the exact same names. For each, group by, take while, drop while, they're all exactly the same. And there are some Scala-specific things that we can't do without implicits. So we can't have a method that, like sum that works the same way because we can't take any evidence in. But for the most part, you can accomplish the same thing with either library. In terms of performance, there's two very important features. They both support lazy evaluation and parallel lazy evaluation. I'm going to be talking about specific differences between them though. I'll talk about Scala's persistent data structures. I'm going to talk about the difference in the hash table implementations, mutable and immutable. I have a short section about primitive specialization, and then I will talk about parallel collections and fork join. Okay, persistent data structures. I will talk about mutable data structures more, but they're largely more similar. The immutable collections are very different between JS Collections and Scala because in Scala they are persistent, and in JS Collections they are not. So a lot of you will know what persistent data structures are, but I'll start with a definition. According to Wikipedia, it's a data structure that always preserves the previous version of itself when it is modified. And I'll put modified in air quotes because they are immutable. We don't really mutate them, but operations yield new updated data structures when they're modified. The typical examples are list and sorted set, and list is beaten to death, so I'll talk more about sorted set. We add by constructing, simulate addition by constructing log n new nodes from the new leaf to the new root. So that means in Scala, a sorted set is a binary tree. In JS Collections, it is not. I'll cover that in a minute. So here's what that looks like. You have a tree with structural sharing. The black tree is, it has the letters A through H, and we want a new updated one that includes E. And so we have the new blue nodes from the new root to the new the new leaf to the new root. And nodes that don't change, like B, are just shared between them. List is the other one, the other typical example where we prepend by constructing a new head in constant time. So in Scala, the immutable list is a linked list. In JS Collections, it's just array backed. a trimmed array. Persistent data structures like these are extremely important in purely functional languages like Haskell. In Java, we've never had that kind of culture, and they're not quite as important, but they're getting more popular. In a language like Haskell, in pure code, all collections have to be immutable, and so you must have good runtime complexity in those collections, or your algorithms that you build on top of them will not run quickly. We've never had them in JS collections, partially just due to history. We wrote our immutable collections before the current generation of persistent collections were popular, but nobody seems to miss them too much, and they're able to solve their problems with the mutable and immutable collections that we do have. So my proposal would be in one library to have mutable structures, the same as they always are, and then persistent and non-persistent immutable collections in the same library. So persistent data structures you would continue to use when you have a use case for structural sharing, but plain old immutable data structures would be useful in other situations, either when you have a load phase in your application, and then once everything is loaded into memory, you can freeze it, or you just load some constant reference data that never changes for the lifetime of your application. So why bother when plain old immutable data structures can't support adding quickly? Well, they have speed benefits for almost everything else other than adding and removing, and there are huge memory benefits. And in the applications that I work on, the memory benefits are the crucial part. A lot of the times when you have immutable data structures, they last a long time. They could be your core reference data that lasts for the life of the VM. They never get garbage collected, so they make it into the old generation. And if we had a way of tagging in the JVM that this data is immortal, we would like to do that, to say that this stuff's never going to get collected. In some of the large in-memory cache applications that I've worked on, memory is the biggest concern. And so when we have a time memory trade-off like this, we will usually go for the big memory benefits that we get. So I mentioned that the immutable list in JS collections is just array backed. Since we know it's not going to grow, it's a trimmed array. Compared to linked list nodes, an array just uses 1/6 the memory. And of course we can support random access, we're going to have good cache locality, and it should parallelize well, most importantly. This memory chart shows the growth in, as the collection gets larger, how many megabytes each takes, and this is pretty straightforward based on what I just described. The blue line at the bottom is for JS collections, and if I had plotted an array, it would be the exact same. It's only different by a constant number of bytes. The array buffer has the characteristic growth of a vector where it's flat for a while, and then when it's full, it doubles in size. And then you can see the linked list at the top uses much more memory. I wrote not only memory tests, but performance tests using JMH, Java Micro Benchmark Harness. And I have a lot more tests than I will go over in the talk today. But all of the tests are open sourced along with the library in GitHub. So feel free to check them out. Before writing JMH tests, I have my performance assumptions going in, and they can be biases, so I don't like to ignore them. I just like to think of them in advance. And in this case, my assumptions were iterating through an array should be somewhat faster than iterating through linked lists, and that linked lists wouldn't parallelize well because they're not random access. We don't have a way of forking it because we can't just jump right into the middle of the list. And in this case, there were no surprises in the results, and when none of my assumptions are violated, I like to just skip it. We'll move on to more interesting tests, but you can find those tests in GitHub. Okay, I mentioned that our sorted set, our immutable sorted set, is not a tree. Instead, it's just also backed by an array, a sorted array. And that means that contains, for example, is just a binary search. We're able to do this because we don't support constant time adding, and so we don't need to be able to add into any location, any random location. Since it's immutable, it's a trimmed array, it's sorted obviously, and since the nodes in a linked list are smaller than the nodes in a tree, in this case we get an 8 times memory saving, which is quite big. And it's array backed, so same benefits as before, good cache locality, it should parallelize well. This memory chart shows what I was just describing. On the bottom we have the JS collections sorted set, which is again the same size as an array. Both of the Scala trees, the mutable tree set and the immutable tree set, have the same internal structure, so both lines overlap here. And that's because they both are built by nodes with a left and a right child and the element itself. The JS collections mutable sorted set has a performance problem, which you can see here, a memory problem rather. We don't have our own implementation of a tree. Instead, we are backed by a Java Util tree set. And that tree set has a performance problem in it. It is backed by a tree map. So our nodes have a left and a right and a key and a value where the value is unused. So in order to bring this line down to, to be equal to the two Scala ones, we need to implement our own tree. Next, I wrote performance tests using JMH, and I wrote a bunch, but the two I'll talk about are contains. I just wanted to check contains, and I also wanted a pattern that would iterate over the entire set. So when testing contains, I figured it would probably be faster for an array-backed version because of good cache locality, where we're just doing a binary search. And I figured that all of the tree implementations would be about the same because they all have such similar structure in their nodes. And my assumptions were not quite correct here. In fact, our immutable sorted set here is a little bit slower. This is measured in throughput, so it's millions of operations per second, millions of calls to contains per second. And for JS Collections Immutable, it's slightly lower. And I didn't dig too far into binary search to figure out why. Because in this case, they're all actually within 10% of each other. And when I write performance tests like this, I'm looking for huge differences, not minor ones like this. Like at least double or half, because this is a micro benchmark. You're not going to call contains in a tight loop in your application, and so it's not necessarily realistic. So moving on, I also wanted to test iteration through the whole thing. So here's the code example for Scala first. And I'm starting with a sorted set that has 1 million elements in it, and I want to iterate over the whole thing and do a few things in lambdas. So it's kind of a contrived example, but I'm filtering out one out of 10,000 items, mapping each int to a string, and then map back to an int, and then count, filtering out another one out of every 10,000 items. The predicates I chose to only filter out a little bit because I want most of the collection to pass through unchanged. And besides that, there's two other important things here. I start by opting into lazy evaluation with view. That's important because if I created intermediate collections as results from filter and map, that would dominate the runtime. And then also I terminate with count because that's a fast operation, and I want to mostly measure iteration, not creating a list or a buffer at the end. Here's what the same test looks like in Java for JS Collections. It is one-to-one, but we've replaced view with as lazy, filter with select, map with collect, and count looks pretty much the same. My assumption about this test is that iterating over the array should be somewhat faster due to cache locality. And in this case, it was true. Iterating through the array was slightly faster. But again, I'm looking for big differences. And at least in serial, there were no big differences. Next, I wanted to check parallel. So to do that, I just replaced view with par, very easy in Scala. And in JS Collections, I replace as lazy with as parallel. We don't default the executor service and batch size for you, so you have to pass them in. And by default, I'll just pick an executor service with one thread per core on the machine. And unless I have a reason to choose something different, I'll just throw in a batch size of 10,000, which is what I did in this test. And this was my first big surprise where, well, I should say my assumptions first. I figured that the Scala tree would parallelize moderately well. Since it's a tree, I can do fork join on that and fork on the left and the right. And I wrote the implementation of the JS Collections parallelism for the sorted set, so I know it just chunks up the array, it'll count in each array, and joining the intermediate counts is very fast, so I knew that would parallelize very well. And here are the results. So for JS Collections, we're getting an almost perfect 8 times speed up on an 8-core machine. And in this case, Scala is actually slower in parallel than it was in serial. So why is that? Well, I took a look at the immutable tree set, and it doesn't actually override par. So it's just inheriting it from a superclass where it just iterates from the front. And then I was thinking, why doesn't it override par? And I'm not sure, this is my speculation. But I think it's because certain operations on a tree are actually quite hard to parallelize. And filter is a good example. You might wind up filtering out the root, and then you would need to pull up nodes from underneath. Or you could filter the left subtree much more heavily than the right subtree, and then you would need to rebalance. And the rebalances might not be a constant number of rotations. So some operations like filter are quite hard to parallelize. But other ones like count should be parallelizable. And my hope would be an implementation of par that is at least no slower for methods like filter and is faster for things like count. So once I saw this performance of the immutable sorted set, I figured that the mutable trees wouldn't parallelize well either. And that was in fact the case. For the mutable sorted sets, both of them are actually slower in serial than in parallel. So for GS collections, we have a performance problem here as well. And it's the same one I mentioned before. We don't have our own tree implementation yet. And so since we delegate to Java's tree set, we don't have access to the left and the right, and we can't parallelize. So 2 follow-ups here. For GS collections, we need our own tree. And for Scala, I would hope to override par in a similar way as we do in GS collections in the future. So to wrap up about persistent data structures, my proposal would be to have mutable, persistent, and plain old immutable data structures all in the same library. I think all 3 are useful in different cases. It's speculation on my part how popular they would be if all 3 existed in the same library, because I haven't seen it done yet. But I believe that in a lot of the use cases for persistent data structures, plain old immutable ones could be used instead, and it can have pretty broad performance impact on your application if you use it widely. Any questions on persistent data structures before I move on? I'll also break for questions at the end. Okay, so next I'll talk about hash tables. And I'll talk about mutable and immutable hash tables, but I'll just start by mentioning the immutable hash table is another persistent data structure in Scala. The immutable hash map is a hash array mapped tree, a retrieval tree. And the way it's actually implemented is in the tree, each node has 32 children. The hash code is taken and split into 5-bit chunks, and each 5 bits represents a number that tells us which of the 32 children to navigate to. We can split the hash code into 7 pieces, and so it means that the tree is no deeper than 7 ever. So we don't say it's log n performance because it's just log 7, we just treat it as a constant. According to Wikipedia, it achieves almost hash table-like speed while using memory much more economically. So I have tests for speed and memory, so we'll see. Moving on to mutable hash tables. The mutable hash map in Scala is backed by an array of entry pairs. Each entry internally holds a key and a value and a next pointer. That's used to point to the next collision in the case of hash code collisions. So this strategy is called chaining because we have like a linked list of hash code collisions. Java Util hash map is similar. It's also backed by a table of entries, and in this hash map, each entry has the key and the value, of course, the next pointer, and it also caches the hash code. So that's an interesting time memory trade-off. When you cache the hash code, it of course takes more memory, but you can get a big speed benefit when you have to resize the whole map. So after you put a whole bunch of elements into the map, it'll fill up to its load factor, and you need to double its size. And at that point, you have to rehash every single element to find the new bucket that it winds up in. And if you've cached the hash codes, you can save a lot of speed. On the other hand, if you really care about performance of your map, you'll probably pre-size it if you know how big it's going to get. And in that case, you're wasting space caching the hash code because you were deliberately avoiding resizes. So unified map is our immutable map, and we chose not to cache the hash code. In fact, we don't use entry objects at all. It's just backed by an object array that's double the length, and it has key values alternating in it. We deal with collisions by replacing the key with a sentinel that indicates there will be collisions, and then the value becomes an array, which in the ancillary array we also alternate keys and values. Our immutable map is another plain old immutable data structure, not a persistent one. And it's implemented by just delegating to a mutable map that it contains, but it's a copy that's completely encapsulated, so it really is an immutable data structure. And that means that its performance and memory usage is going to be the same as on the mutable side. So this chart shows the memory usage, and you can see a few of the things I just described. Up at the top is the persistent data structure, the immutable hash array map tree. So it is actually quite expensive in terms of memory in those nodes. All of the other maps follow a similar pattern where there's a gentle slope while they're growing the number of collisions in the map, because they all use chaining for their collisions. And then there's a steeper slope at the resize points, like here. Oops. Sorry. And there as well. Both of the JS collections maps are on the same line because the immutable one delegates to the mutable one. Scala's is taking a little bit more memory because of the entry objects, and Java's is taking a little more memory because the entry objects cache the hash code. So in this case, my follow-up, I would like to just take the guts of Immutable Map and port them right into Scala's map. I'll talk about performance as well, because you need to make sure that you're not hurting performance just to improve memory, but I believe that is the case. And I actually tried to do this. I got pretty far with it on my own. I got up to the point where all of the methods were implemented, and the only thing I had to do was share state with the parallel collections, which is different than how we do it in JS Collections. So I ran into a little bit of trouble there, but I think that with maybe a little bit of help from a collections expert, we could port the body of unified map into Scala's hash map and bring the red line down to be equal to the blue lines. Next, I wrote some performance tests for get and for put. And here's the code. I wrote these all in Java, actually, even though this is a test for a Scala map. And I tested for a number of different sizes. The reason I tested for different sizes is to check for two effects. One is for very small maps, you get weird results in a benchmark because the entire map is pulled into cache, which doesn't usually happen in production. And the other thing is I wanted to see what would happen with the sizes when they were near resize points, when the map doubles in size. For the Scala map, I check is defined because it's returning an option. The code for JS Collections would look the same except there would be a null check there. And here's the performance I got for get for different sizes of collections. We see that for very small ones we get very different performance because it was pulled into cache. And for three of the maps we get these performance boosts around resize points, these bumps. And that's because right after a resize, just above that point, the map has a lot fewer collisions in it, and so get can be a lot faster. At the bottom we have the immutable persistent structure. So there is a performance penalty as well as a memory penalty for using it. Both of the JS Collections ones are about the same except for some jitter, and that's expected since one delegates to the other. And the Scala map is pretty close. It's a pretty good implementation in terms of speed, but I never found it faster, and so I don't really think that there's a downside of porting the implementation of unified map into hash map. The reasons that it's slower are a bit hard to isolate. It could be because of the entry objects. It could be because it returns options, but it's really hard to isolate them without actually changing the map. I tested put as well, and the first thing to notice here is that there's even more of a runtime performance penalty for the persistent data structure, for mutation, than for lookup. And besides that, I'm seeing basically what I would expect. I still see performance bumps around resizes. But there's one other thing I had to do here to make this fair. I figured in a performance test where you care about put, you would pre-size the map. So I pre-sized the JS Collections and Scala map. But I had to jump through some hoops to pre-size the Scala hash map. Here's what the test looks like. I wrote my own subclass of hash map called presizable hash map. And I'll show you what that looks like. I had to try a few different things to get this to work. The hash map looks like it's designed for extension because it has a lot of protected fields like table and threshold and initial size. But even though everything in it is protected, when I looked inside resize to make sure it wasn't being called, it was in fact being called in my first few attempts. And so this is what I wound up with, where I actually just let the superclass constructor do what it's going to do. It initializes a table of size 16. Then I throw it away, and at the bottom I reinitialize the table to a big array, and I have to recalculate the threshold that's the size at which it will next resize to be bigger by the load factor, and that's just to make sure it's not less than the size of the table, so it never resizes during my performance test. So this is a very clear follow-up. I think that the hash map in Scala ought to just expose a constructor that takes an initial size, and we need some tests to make sure it really doesn't rehash ever when you grow up to that size. Moving on to sets. In a lot of ways they're similar, but the mutable set in Scala is backed by an array, and it handles collisions by just putting them into other slots in the array. There are no entry objects here. So this strategy is called open addressing as opposed to chaining. Open addressing is fine. If I had more time, I could talk in detail about the differences between open addressing and chaining, but they both can perform quite well. I was just surprised to see open addressing for the sets and chaining for the maps, because in all of the collections frameworks that I've compared against, they make one choice and use it across the board, except for Scala. But the performance winds up being okay, as you'll see in a minute. Java Util hash set, I need to mention, it's really poorly implemented because it is backed by a hash map. And so that means it has an entry object still, as I said before. And in the entry, the key is used and the value is not used. And so instead of double the memory usage, it's actually 4 times the memory usage. So it's quite bloated. In unified set, we do use chaining. So it's just backed by an object array. And in every slot, there's either the element or an array of collisions. And again, the immutable structure just delegates to a mutable one. So it's a plain old immutable data structure. And here we see the memory usage. At the top, we have kind of overlapping and crossing with each other, both the Java Util hash set, which wastes memory on entries, and the immutable hash array tree for the hash set, the immutable hash table. So they both use quite a lot of memory. Both of the JS Collections ones overlap again, and the Scala one has a different growth pattern than before, where we see the characteristic growth of open addressing with flat line when we're adding collisions. Since they go into the array, they don't take any extra memory. And then when it resizes by a full 2x. But on average, you can see that it's similar. And in terms of the performance, the hash set was similar as well. Okay, any questions on hash tables before I move on? Okay, I have a short section on primitive specialization. There has been a lot said about primitive specialization, and I don't want to repeat too much of what has been said elsewhere. I really just want to focus on how it affects collections and memory usage. So we know boxing is quite expensive. You pay not only for the reference, but the header and potentially alignment as well. And Scala does have specialization where you opt in through the specialized annotation, and it's done by the compiler. But most of the collections are not specialized, and I don't think they can be specialized. They shouldn't be specialized, because they're implemented in a way that uses either sentinel objects or null checks or other things that mean you can't use specialization. And so if you cannot afford to pay the memory cost of a wrapper, then you have 2 choices, that I see anyway. You can just use primitive arrays, and that will work okay as long as your use case is for a list. But you're kind of out of luck if you want a primitive set or a primitive map where the values are primitive. So your second choice is you could just use a Java library, and I see people do that. They use JS Collections for that, or another popular one is Trove. And that works. You know you're going to get the performance you desire, but there's a few things that make it feel like not like Scala. You have different method names potentially. You're not going to get the familiar filter and map. They'll use their own types for the functional interfaces, like we have our own predicate. It's not going to be using Scala's function 1. And that means it's not really going to work well in a for comprehension either. So I have a quick memory chart. We know that boxing is expensive. The only thing I wanted to really point out here is that unlike the previous charts where I showed memory, in the previous charts I only showed the usage of the collection itself. I didn't count the strings or whatever I was putting in there. Here it's fair to count the integer wrappers because you would not have them in your heap at all if you were using a primitive collection. And so the 2 lines here for the unified set holding integer wrappers and the mutable hash set holding integer wrappers are higher than they were before compared to our primitive int hash set in JS Collections. So my proposal would be to add primitive lists and list sets and maps into Scala. I would rather not wait for this stuff to be implemented or solved for us in the JVM itself. Oracle will release Java in the future with value types, but it sounds like that won't come until Java 10, which is years away. And I would say that for now it makes sense to have primitive collections in Scala as a choice to use. There's pros and cons of this. The obvious pro is it's for performance, but the downside would be it's not a traversable. It's outside the collections hierarchy. You wouldn't have the nice type unification, so we'd have to think about that carefully. And then the other thing is that, one thing which would work nicely is you would have all the methods that you're used to that I mentioned before, like filter and map. And presumably we could get that to work well in for comprehensions as well. But I think that we would need function specialization to work better than it does today. I think that work is known. It's just probably not high priority at the moment. But the function interfaces like function 1, function 2, they are specialized in the source code, but I think that boxing still happens in a lot of cases in the bytecode. Okay, so that's it for specialization. I know that that stuff might be tough to change. All right, fork join and parallel collections. I wrote this performance test that's similar to the one that we looked at earlier, but now we're doing it in parallel. And earlier I was terminating an account. The difference here is I want to focus on, in fork join, the join step, so I want something more significant than the integer count that we had before. So in this case, when I terminate with toBuffer, I'm going to have intermediate buffers that I need to call add all or something like concatenate to get them all into a single buffer. Here's what the same test looks like for JS collections. We have as parallel at the beginning instead of par, filter becomes select, map becomes collect, and then we terminate with toList here. I have the same test for Java's parallel streams in Java 8, and we start by calling parallel stream. The methods look very similar to Scala. We have filter and map, and then we terminate the stream with collect, and we have to pass in a collector to say how, and in this case I want the collector called toList. That tells us we want to get back an array list. So here's the performance I got for this test in serial and parallel. In serial, all three were about the same. In parallel, JS Collections is getting an almost perfect 8 times speed up on an 8-core machine. Java's parallel streams are getting about a 6 times speed up, and Scala's about a 4 times speed up. So why are Java and Scala's not scaling quite as high? Well, I didn't really talk about the way that join works. You have choices here, but the way that join is implemented in both of them is by joining intermediate results in a tree-like shape, where they double at each level of the tree. So merging is a total of n log n work and garbage, but that work is spread across the whole thread pool. Until you get to the point where you're merging 2 halves into one whole, and that has to be done in one thread while the other cores are idle. This, I believe, is the primary reason that in this test, Java and Scala are not scaling up quite as high. So how do we get around this in JS Collections? Well, in toList we do something special. Normally you would expect us to return a fast list, which is our vector type. Instead we return a composite fast list, which is optimized for combining into. Specifically, it has a constant time implementation of add all. And we do that by having composite fast list just delegate to a list of lists, which we add to one list in add all. And you can imagine the performance implications of this. The major downside of this is that get is no longer really a random access. If you wanted to jump right into the middle, for example, in this case we have a list of size 1,000,000. If you wanted to jump to 500,000, you'd have to first iterate through 50 of the backing lists. And just to make those numbers concrete, in the test we started with a list of 1,000,000. I had batch sizes of 10,000, and so my composite fast list at the end will have 100 batches in it of size 10,000. So for get in the middle, I would need to iterate through 50 of the lists. On the other hand, almost everything else that we do with this is quite fast. Iterating through the whole thing still is very fast with for each or select or collect. So even though there's performance pros and cons, in the applications that I've worked on and where I've used this, it's scaled up better than the alternatives. An interesting side effect is that since merging is the merge work is constant time, we don't even bother parallelizing it. We just do it in the original thread, not even in the thread pool. In this case, it's just 100 calls to add all. And so it's very simple. Of course, this will only scale up to a certain point as well, and I think that when we have machines with hundreds or thousands of cores, we'll have to revisit this, of course, but at the moment, this approach is scaling quite well. So the takeaway here is that fork join is general purpose. You can imagine how to implement almost any kind of algorithm in parallel using fork join, but it always requires merge work, and depending on what you're doing in the merge step, that step can be quite expensive. And we can get better performance through specialized data structures meant for combining into. It is difficult to replace something that already exists, like the parallel collections today, to return a new type, because it would have different performance pros and cons and would affect existing code. But I do think it's worth considering, because in some cases the scale up is much better. All right, so we talked about persistent structures, hash tables, primitive specialization, and fork join. I just want to point out where you can go for more information. You can reach out to me directly, of course. If you're interested in to learn more about JS Collections, you can ask us questions on Stack Overflow. We watch for the tag JS Collections. All of this stuff is open sourced. We have 2 repositories open sourced. So we have the main library, JS Collections. All of the performance tests here are in 2 test suites called JMH test and memory test. We've also open sourced our training material, which we call the JS Collections Kata. And that's set up as a series of unit tests that fail, and you get them to pass with things that you learn about JS Collections. I think it would be very easy and fun for this audience, because if you're already familiar with the Scala Collections library, it'll feel familiar to you. And I just want to point out, I gave another talk last summer at QCon that focused entirely on today's last section, parallel lazy collections, and I went over more algorithms, including a detailed look at parallel map algorithms, where we aggregate into a map. So if you're interested to find out more about parallel lazy implementations, please check out that talk, that video on InfoQ. We also have the JS.com engineering site, where it has some more information about JS collections, as well as other interesting engineering problems that we solve at Goldman Sachs. All right, with that, I'd like to open it up for any questions.
Scala now has an anyref map and a long map in the mutable collections. I wrote those specifically to increase performance. Have you tried them out and see how they compare?
I don't have as detailed performance comparisons there, unfortunately. The long map is immutable, right?
So they're both mutable. So the immutable collections had an old set of maps specialized for integer keys or long keys. But I'm in, I think it was it 210 or I don't even remember anymore. Anyway, at least in 211 there's the anyref map and long map in mutable maps, which are introduced to try to recapture the performance that you see with Java hash maps, which under a number of conditions could be better.
Okay, so I need to look at that more closely, and I think that will be very good for the use case of a primitive to object, right? Long to anyref?
So the long map has long keys and object values. The anyref map has anyref keys and object values, which is actually valuable because one of the overheads you have when you have an any is you have to figure out if you need to do a complicated comparison with an integer, where you don't want to compare the references, you want to compare the values, and so you've got a whole bunch of extra logic there hidden, which Scala very helpfully hides behind an equal sign. Very convenient, but it's a lot of extra logic. So if it knows in advance that a key is anyref, like if your maps are strings, keys, it actually can improve performance a fair bit.
Okay, so I'm not sure if I can fully answer your question because I don't have as many performance tests as I really need there, and I'll have to follow up on that. I'll just mention that in JS Collections we have, we code generate, which is a bit unfortunate, maps where the keys are either objects or primitives and the values are objects or primitives. So we have all 4 combinations and for all 8 primitives, and so the byte code is huge for that, as you would imagine. I think it's half the size of our jar is just taken by the primitive maps. But you know, mapping from a primitive to a primitive, you can get a lot of memory savings by doing that.
Now your lazy collections, your parallel lazy collections, the tests where you're on JS Collections using as lazy and then saying filter map to list. To me that's not a direct comparison with the Scala parallel collections where you just said .par, because Scala is not treating those steps lazily and fusing them. Are you aware of that?
Yeah, well, we don't fuse them either. I mean, each lambda still gets called in a row. But
you've got a
sorry, are you saying that for Scala, if you do, it'll do a parallel filter, finish that, then do the parallel map?
Yeah.
Okay, I wasn't actually aware of that, but that's, in my opinion, a performance problem that we could fix.
Yeah, so depending on your use case, one thing you can do is sort of say a 2-iterator and then fuse all of the filters and maps and then say .par to build up the rest. And so there's different ways around that. The second point is just for people who are looking at the use of using .view to get that fusion in the sequential case. it's simpler and often preferable just to use .iterator for that case. Views give you richer semantics, like they kind of can maintain the setness of the collection, but there's a lot of machinery behind them, and simply calling .iterator is much easier to reason about.
All right, thank you.
Yeah.
In our case, for the parallel lazy collections, I think they are similar to what you described as the serial views, in that they maintain the notion of whether they have duplicates or not, ordered or not. So that's in JS collections anyway.
Okay, cool.
All right, thank you. Any other questions? All right, well, thank you very much for coming to this talk.